5.4 Logarithmic and Logarithms and Logarithmic functions. Okay, so we're going to relate a logarithmic function and a exponential function because they are very much related. So first off, let's look at this exponential function. We can tell that it's increasing because my base is 10. We'll have an x-intercept of none because there's no x-intercepts, and the y-intercept will be at 1 because that is my value in front of the 10. It will have an asymptote at y equals 0, and it will have a domain of element of the real numbers and a range of greater than 0. So let's plug this in. So we have -2, so we have 1 over 10 to the power of 2, which is 1 over 100, which is 0.01. We have 1 over 10 to the power of 1, so 0.1. We have 1. 10 to the power of 1 is 10. 10 to the power of 2 is 100. Alright, now what I want you to do is I want you to type into your calculator for the logarithms. And your calculator, what you'll notice, is just has a log button. So this is called the common logarithm. Anything with a base 10 is the same as writing log without it. So our calculator will only do log base of 10s. They'll also do natural logarithms, but that's not really necessary right now. And so when you type it into your calculator, you're doing the right thing automatically. So we have -1. You should try typing this in, and what you should notice is that it says error. So that means it's undefined, and it will also be undefined when you hit 0. So I want you to pause the video, and I want you to fill in the rest of this chart. So what you should have got was -2, -1, 0, 1, and 2. So just some things about this. We're getting negative and then we're getting more positive, so I can tell that this is increasing. I also can see that this has a base of 10 because that little number is also called a base in a logarithm. I can see my x-intercept is 1, and because when I plug a 0 in for x and it says undefined, we're not going to have a y-intercept. So that means that it's an asymptote at x equals 0. Our domain, because it won't let you go negative, is going to be greater than 0. And I'm just going to take a guess that the range is everything. And the reason I'm saying that is because if I look at all of this information, everything is opposite of one another. And the reason why is because they are inverse functions. They are inverses of each other. So that means when I graph them, they're going to be symmetrical on that diagonal. Right? Because that's how inverse functions work. So if I plot my points for my exponential function, it looks like this. And for my logarithmic function, it looks like this. So they are definitely inverses of one another. So this becomes useful for us because that means we can exchange and not exchange, that's not the right word. We can change forms from logarithms to exponentials very quickly and very easily, and vice versa. So the way that it works is your b remains the base no matter what, and then we flip our x and our y positions. So for the first one, we're going to rewrite this as a logarithm. So we're going to say log with a base of 3 because it's still a base of 3. And now on the equal signs, we're going to flip where the numbers are. So 27 is going to come to this side, and 3 is going to come to this side. This is the same as thinking 3 to the power of 3 makes 27. The next one would be log base 5. The base stays the same. Now we're going to put 1 over 25 on this side of the equal sign, and negative 2 goes over here. So 5 to the power of negative 2 makes 1 over 25. Last one, log with a base of 4. My base stays the same. The 1's going to move to this side of the equal sign, and the 0 will move over here. So again, 4 to the power of 0 equals 1. Let's go backwards now. So we're going to start with the base. So 3 to the power of 4 makes 81. That's how we evaluate that. 5 to the power of 3 makes 125. 6 to the power of 0 makes 1, and it works both ways. So let's use this to evaluate some logarithms. So we have log base 5 of 3,125. So this is the same as saying 5 to the power of what equals 3,125. So I'm going to start by taking 3,125, and I'm going to divide by 5 until I get to 1. And it's going to take me 5 times to get there. So 5 to the power of 5 is equal to 3,125. So we know the answer is 5. So we're going to show this by converting. So we have log base 5, and instead of writing 3,125, I'm going to write 5 to the power of 5, and I'm going to make it equal to x. And now we can convert. So 5 to the power of x equals 5 to the power of 5, and then we can cancel out our bases to find that x equals 5. For the next one, we're going to change that 216 to be 1 over 6 to the power of 3. I then can change it to be 6 to the power of negative 3. So we want to think about this as 6 to the power of what equals 6 to the negative 3. We can cancel our bases to show that it is negative 3. Now the last one's a little bit different because it has a base of 8 and everything else is 2. So I'm going to first start by making this 8 a 2 to the power of 3 because that is the same as 8. And then I'm going to convert this to be 2 to the power of 1 times 2 to the power of 1/3 using my exponent laws. And I'm going to simplify that into saying 1 plus 1/3, which is 4/3. So now I want to think about it as 2 to the power of 3 to the power of what equals 2 to the power of 4/3. Cancel out my bases. I have 3x is equal to 4/3. Divide both sides by 3, and I get that x is equal to 4 over 9. So that one had a little bit more steps than the last one. Okay, to the nearest tenth. So actually, we're going to say hundredth. Tenths is not good enough. That's not even how you spell hundredth. Whatever. We're going to evaluate log base 5 of 100. So there's no 5 to the power of what makes 100, right? Exactly. Not like a whole number. So that means we're going to use a decimal. So I'm going to use my brain here. So I know, use your brain. Shocker. 5 to the power of 2 I know is 25. And I know that 5 to the power of 3 is 125. So if I want 100, it's going to have to be between 2 and 3, and it's going to be closer to 3. So let's try 5 to the power of 2.8. So if I type in 5 to the power of 2.8, I get 597. Let's see if we can get closer, because I feel like you can get closer than that. So 5 to the power of 2.9, I get 106.417. So that's too far. So we know it's going to be between 0.8 and 0.9, and it's going to probably be closer to 2.9. So let's try this now. So we're going to go 5 to the power of 2.8, I don't know, 5. Let's try 5. If I try 2.85, I get 98.189. So that's pretty close, but I bet we can get closer. Let's try 5 to the power of 2.86. For this one, I get 99.782. We're probably not going to get closer than this, but let's try 2.87, and you get 101.401. So this is as close as we can get to the nearest hundredth. So we would say log base 5 of 100 is roughly, approximately 2.86. And that is how you'd estimate that without having to actually type in the logarithm itself. Okay, let's graph log base 4 to the power of x. So graphing logarithms is actually the absolute easiest thing to graph. And we're going to just first think about it as an exponential. So if I wanted to graph the exponential that matches this, it would be 4 to the power of x. If I plugged in 0, 1, 2, okay, so if I do this, it would be 1 over 4 squared, so 1 over 16, 1 over 4 to the power of 1, so 1 over 4, 0 and 1, 1 and 4 and 2 and 16. So I'm actually just going to focus on these 2 points right here. Because when I graph now log base 4 of x, we would invert them because they're the inverses. And we'd have 1/16 and -2, 1/4 and -1, 1 and 0, 4 and 1, and 16 and 2. But these points right here are really important because it's our x-intercept. So if you have a function in this form, y equals c log base a of x, and it hasn't been translated or anything like that, you are going to have an x-intercept at 1 and 0. So you plot 1 and 0. That looks terrible. So we'd have 1 and 0 right here. And then you will have a point at whatever your c value is and your a value right there. So it's at a comma c. So we will have a point at 4 and 1 because this is 4 and there's a 1 in front of here. So I would go right here to that, and then you just connect. So yeah, graphing logarithmic functions is super easy. I'll give you another example. If I wanted to graph log base 5 of x, I'd plot my point at 1, and then I would go to 5 and 1. Oh look, it's done. Yay! I love graphing logarithms. They're awesome. Okay, bye.